Hello kids, this is going to be the second part of the thermal block. We will be discussing modes of thermal exchange. We have previously completed our topics of thermal capacity, how heat is transferred from one object to another, and what it means to have the kinetic energy in the particles when they're conducting heat, right? So we have discussed all these things. Now we're just going to cap it up with the modes of thermal exchange, right? So let's get into it. Thermal exchange, how objects or mass can exchange thermal energy, right? Now there are three modes. We namely call them conduction, convection, and radiation, right? Okay. So what is conduction? Conduction is a property of usually metals, right, and solids, in which they transfer thermal energy from one point to another within that material, right? So let's see, we have a metal bar over here in which we see these particles which are vibrating back and forth, right? They're matter particles. They cannot move around because they're fixed in their position, so they have vibrating motion. We start to heat up one end of this metal. We would find that the particles at that end, at the left of it, let me grab my pen. Okay, at this point you can see that the particles are now having higher amplitude as compared to these particles. Why? Because we're heating at this end, so thermal energy is flowing from our source, whatever it may be, let's say a Bunsen burner or a lighter, right? We heat it up. It will the oscillations of these particles will increase, so it will hit other particles, neighboring particles, transferring their energy to the next one, and this will keep on going till all of this metal bar is at a higher temperature, right? Let's say if we're giving this metal bar was at 25 degrees Celsius, right? Initially, let's call it T1, right? Then we heat it up to T2, right? Let's say 100 degrees Celsius. We're just giving it thermal difference of 75 degrees Celsius, right? We're trying to heat it up to 100 degrees Celsius, and we place the thermometer over here, right? We have a big thermometer, right? We attach it to this metal rod, and we try to measure at initially for quite some time. Let's call T, right? T minutes. We stop our stopwatch, and we measure how much time it will take for this end to be fully heated up, right? So as we see that there are many, let's say this is at 0 degrees Celsius, so we will have our initial T1 somewhere here, right, at 25 degrees Celsius, and then let's say if this was the 100 degrees Celsius of the thermometer, we would find that it would rise in the scale, right? But it would take some time. Why it would take time? Because these particles they will attain energy slowly, right? It doesn't mean that it is just going to, once we start heating up, the other end is going to heat up immediately. No, it will take some time. Why? Because these initial atoms will require some time to attain certain amplitude at which they are able to collide with the neighboring particles, right? And then those will also increase in amplitude, and later the next and keeps on going forward, right? So as a whole, if you move forward, they start pushing each other around, and this is how the thermal energy is transferred from one end, right, over here, to all the way to the other end, right? It takes certain time, and that way we can evaluate how fast or how slow a metal bar, any different metal bar, let's say we have copper, we have brass, and we have steel, so we can differentiate how much time it is going to take for these three different materials to heat up from one end to another, right? That is what we call as the rate of conduction, right? And this is how you will say that thermal energy was transferred from one bar to another, right? So as we perform this experiment, we can list down several factors of why and how this thermal conduction occurs, and what are the factors that will affect the rate at which this conduction is occurring, right? So the first thing would be cross-sectional area. If we it is increased, it is going to be harder to conduct electricity, because now there are more atoms in one area to transfer energy. But if we have a thin wire, I think that is going to conduct a little faster, because then we have restriction of the atoms, right? And they can collide their neighboring atoms much more quicker than before, right? And this is how the area is going to affect. In the same way, if let's say if this bar was a small bar, then it would take less time from for the heat to travel from this point to, let's say, this point, right? But let's say if this was a very large bar, right? If it were longer, then it will definitely take a lot more time for this thermal energy from this end to transfer to the other end. Now over here we also use the term thermal transport, right? This is how we can say thermal energy is transported by a material from one end to another, right? So these are the factors which help us understand how conduction works for different material. Let's look at some examples. We have these metals which are very good conductors, right? Usually we see heat conduction systems usually made out of metals, because we want energy to be transferred more efficiently. An example of a poor conductor, and remember, it is still a conductor. I'm not entirely going to go into just the word insulator, because I tend to consider three different categories of material rather than just saying a conductor or a insulator, right? I also have this gray area which I call poor conductor, but usually poor conductor is used for this term insulator. So we can just simply call slower heat conduction and poor conductors being purely insulators, right? So just use the term insulators instead of using this poor conductor, so that people don't get confused. Okay, so when we look into insulators, we are looking at materials which do not conduct electricity, thermal energy, right? And in most cases, these thermal insulators are also electrical insulators. Why? Because we will shortly review why these metals are good conductors, and why other materials are insulators, because it has something to do with the electrons as well, right? And definitely that is why metals are better conductors of electricity as well. We have discussed this fact several times, that good electrical conductors tend to be good thermal conductors. We'll try to figure that out using the atomic structure, right? Okay, for this polar bear, right, we see that they tend to live in a habitat which is very cold, right? Usually at below the freezing point, and still these animals tend to live there, enjoy their life, right? Roaming around, hunting around. So how they are able to do so, and why we won't be able to survive in that weather, is because they have this natural fur on them, right? It is an organic fiber which is covering their body, which keeps them warm. And why? Because it's an insulator, so their body heat is not radiated outside. Why? Because the fur is protecting their internal body heat to be available for themselves, and does not go into the cold environment. The similar way, it also protects the environmental cold to not lower their body temperature, so they can easily survive in such colds, while we would require similar strategy to survive there, like we wear jackets or overalls or caps and gloves to survive over there. So they have this natural fur on them, which is an insulator. So over here we can say that insulators are those materials which actually do not conduct thermal energy, right? Or even if they do, then they tend to do it very 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 slowly, such that there is very little change in the thermal energy of the object itself, right? Moving on, we have few other examples. As I said, metals are the best conductors of heat energy, right? So consequently, we can surely say that non-metals tend to be better at being insulators, right? They're poor conductors. So if we have a polystyrene cup, we hold it, we do not feel that our hand is now getting any colder, because it is preventing the heat from our hand to go into the environment, right? So we don't get to feel our hands getting cold. Similar example would be these insulator gloves which we use in the cooking, these wooden spatula that is used for cooking. So why these are used? Because this is spatula is preventing from the heat of the stove or the pan to get to our hand. The same is for this glove. Now, this is about solids, right? Solid conductors. Now, if we look into the fact that liquids, they are also having particles which can vibrate, which can transfer energy, but they tend to be poor conductors compared to these solid conductors, mostly metallic conductors, right? And gases are the worst of them all. Why? Because gases are already at higher energy. They will increase their pressure, but they might not be able to transfer energy elsewhere. Why? Because they're absorbing the energy them for themselves, so they won't be transferring much of the energy around, right? So we can use gases as well as insulators, right? So in most cases, we have insulators that have trapped pockets of air inside them, and the biggest example would be again polystyrene. These polystyrene cups are actually made out of a polymer, and then when it's being manufactured, these polystyrene cups, air is actually filled in with pressure into the molten polymer, which when solidifies, the air is getting entrapped in it, and it forms that lightweight foamy kind of a polystyrene cup, right? Okay, moving on, let's test how different conductors can be categorized as better at conduction or worst conductors, right? So uh, let's see. We have four materials. One is brass, aluminum, the third is copper, and we have steel, right? And we simply just spin them around using simple Vaseline or any wax, right? At room temperature, the wax appears to be pretty much solid. So these metal bars are supposedly to stay in their positions. Let's say if it's hung on a wall, and we place a radiation heater in them, right? We are using a radiator, let's say a bulb, right? A tungsten bulb which will generate a lot of heat when it's lit up, right? And the heat is not transferred physically, but instead the light falling onto these pins will provide them the energy. And how fast the radiation energy from this radiation source is going to travel from this point to the other end, to the point where the wax is. It will melt the wax, and that specific material will then drop, right? So if it's a good conductor, the pin should fall earlier, and if it's a bad conductor, then the pin should fall at the last. So considering that, we are going to note that how much time does it take for these pins to fall. So we have copper over here, which is taking just 73 seconds to fall. So copper will be the first to fall down. Why? Because copper is a good conductor of thermal energy. So energy from this light bulb which is falling onto this pin will transfer from one end to the wax faster, so it will melt the wax, and the copper pin will fall, this material will fall, right? The next one is going to be aluminum, which is also a good conductor of thermal energy, so this will fall again. Third would be brass, which is an alloy of copper and zinc, right? This is Cu plus zinc. So copper is a good conductor, but actually addition of zinc makes it a little slower at being thermal conduction, right? So the rate of thermal conduction is less as compared to copper or aluminum. And least is going to be steel, which is in this case going to be the worst conductor of them all, right? Why? Because this will take 340 seconds to fall down, so it is taking the highest amount of time. The energy from this point is taking a lot of time to travel to this point, such that the wax is going to melt and it will fall, right? So as per the textbook that you people are having for the Cambridge, right? Cambridge textbook for physics, IGCSE 0625, we have these values listed in the book, which is 204, 109 for brass, and then 385 for copper, and 16 for steel. And now this is relative conductivity values. Now do not confuse this with resistivity, right? Thermal resistivity is also a thing, but this is conductivity. That means how high or how fast a material can conduct, and we see that copper has the highest conduction rate. Then we have aluminum at second place. Third is going to be brass in this case, and last would be steel, which has the lowest value for the relative thermal conductivity. So uh, this is how we can categorize a conductor which is best at conduction, the faster at conduction, and the one which is worst at conducting thermal energy, right? Okay, one experiment that we can do that liquids are actually bad conductors is that we're going to take a test tube of water, right? We're going to put ice at the bottom, right? And then we're going to seal it off, or put a gauze, metallic gauze or something, which can conduct thermal energy, but it is not going to allow this water to be inside that end, right? And then we're going to fill that test tube with water, and we start heating the top, right? And since energy is entering into the tube uh, through this point only, so it will definitely take some time for it to travel all the way down, and then we'll see the ice melting, right? Even if we're boiling it, we're supposed to see ice melting faster if we have a similar test tube and we just put it aside and compare the time is not going to be that much high. Why? Because initially it will take a lot of time for this thermal energy to get to the bottom. Why? Because most of the energy will be converted into vapors, these high energy particles. As we know, liquids evaporate as well as they boil, and if we're giving a lot of heat, then the water on the top will start boiling. It will take the energy from this liquid out, ensuring that lesser energy is being transferred down. So it will take a lot of time for this ice to receive the energy coming from here and then melt, right? So this is one test we can use to classify that liquids are not good at conduction, right? So this is what we're going to say, that the energy is being transferred very slow, the conduction rate is slow, right? Okay. What are the uses of some insulator materials? Now, we can use insulator materials to, help us with, thermal energy being retained, especially in winters. If you look at our houses, then we have 35% of energy, which is the highest out of the all in the house, being lost through the walls, right? And these are not insulated, right? If we don't have insulation on the walls, it would be the biggest source through which thermal energy is being lost. 15% for the floor, 15% approximately, and these are just approximations, right? And for the doors, and 10% for the windows, and 25% for the roof, if these things are not insulated. Now we cannot insulate the door or the windows, but we can think about insulating the floor, the walls, and the roof, and that would put it a total of 75% of the thermal energy that we can save and reduce our heating cost, right? So if we just put insulation in our house in just the three of these points, then we can actually save a lot of thermal energy and save eventually thermal cost, right? Similar, structures are found in areas which are very cold. You would find these pointy structures, in which are geometrically designed such that if snow falls, then it is forced to go downward rather than being staying on the top and being collected. Secondly, these structures are also filled with some kind of wool, or some kind of foamy material, such that it entraps air, and it becomes a very poor conductor of thermal energy. As well as we put wood, which is also a thermal insulator, so it will try to hold up heat in our house, so we can prevent this 25% with such an application, right? Other way, the windows, if there are some windows which are actually double laminated, double glazed, and they are designed in such a way that heat is not transferred. Why? Because two separate glass sheets are used, in which in between them we either fill in air, right? Or we just remove air creating a vacuum, that would definitely be a perfect example of an insulation. Why? Because when there is no material in between them, so no particle there to collide or transfer energy, so it would be a very good thermal insulation in between them, vacuum as well as gas, right? In terms of walls, we can add in insulation in between the surfaces or on top layer, right? Nowadays we have these beautiful printed panels which we can use on the walls. We can paste them on walls. We can do the styling as well as prevent thermal energy from escaping from the walls, right? So we can prevent quite a lot of energy, approximately 50% of the energy, as well as if we add this 15% from the floor as well, then we can save a lot using carpets or stuff, right? So we can secure a lot of thermal energy using these few materials. Now we also have these geysers, right, water heaters, which we use in our houses, and they're also the water tank inside them, which is being heated, is actually covered by this again mineral wool or glass wool, right, which prevents thermal energy from escaping. Why? Because air is entrapped in between them, and that becomes an actual insulation. Why? Because solid particles would conduct faster, and this air-filled low density material will allow lesser energy to be transported, right? So these are a few examples of insulators and how we can use them and where they're usually used in our daily lives, right? Okay, now as I had previously discussed, that we will get into the atomic level idea of how conduction is occurring, right, and how electrons are responsible, why good electrical conductors are usually good thermal conductors as well, right? So uh, let's say we have a piece of metal, right, in which these are the fixed atoms, right, in which these atoms vibrate themselves, but we also see a sea of electrons, right? We always say that these are the positive centers, and then we have the electrons about them, and some of those electrons are also free to move about. And the more energy we give to these particles, the faster these particles will move, these free electrons, and hence they will transport thermal energy a lot more faster, right? So this is how the atomic structure really affects thermal conduction. So that is why copper, having two electrons, two valence electrons in its metallic bonding structure, like the crystal lattice or the metallic lattice, it is conducting electricity much faster, as well as it is also conducting thermal energy, in this case much faster compared to other materials, right? Aluminum also has three valence electrons, so it is also a good thermal conductor as well as also a good electrical conductor. Steel is again poor at thermal conduction as well as electrical conduction. So why? Because there are also two electrons, sorry, three valence electrons, which are able to move about, but the structure has a lot more gaps in between them, so that's why those electrons will require a lot more energy. Since copper is a dense metal, so these particles have less gap between them. In case of steel, these particles are much larger apart, so electrons will require more energy to jump about, right? It will require more energy to transfer from one point to another, right? Moving on, we have the second mode, which is convection. We have discussed conduction, and we have discussed what insulations can be, right? Now we have this mode of thermal exchange, which we call convection, in which we don't have electrons being responsible for conduction, right, or exchange of thermal energy. In conduction purely, the word conduction, when we say, we're referring to exchange of energetic particles, not the atoms themselves, but these tiny particles, electrons, which drift from one atom to another, carrying thermal energy. But in convection, we actually have molecules or particles themselves moving through the object or our container, that is transferring energy from one point to another. One example would be water. If we have a beaker of water and we just heat it up from one point, we find that bubbles will come out only from that point particularly, and that point would be at boiling point, and the hot bubbles will go up, hot water will be moving up, pushing the water on this surface, which is at lower temperature, around and creating a current of cold water coming back down to the heating source to get heated up again. So this is what we call convection, right? Now thermal energy in this beaker is being transferred. It is a slow process compared to metals, but it is being done by the particles themselves, right? So in convection we have uh, you know matter particles, or mass particles, which move about, especially in case of gases and liquids, right? So both of them are involved. That way we will have convection, right? Okay, remember, whenever we heat these particles, we do know that they have more kinetic energy through the kinetic particle theory, right? So these particles will start to move much faster, collide with one another. This causes expansion in liquids as well as in gases. In other words, when things will expand, these gas and liquid will expand, their density would be lowered, and we do know that lower density tends to be moving upwards, and higher density will be moving downwards. So when this water is heated up, so hot water gets less dense, it rises upwards, while the cold water on the surface or anywhere else is going to move downwards. It will create this current, right? So it is actually the expansion that is causing this current to be there, right? Moving on, we have this clear example in which during the day, when the sun is shining, the air around the surface of the earth is heating up. It moves upwards, while the cold air at the higher atmospheric stages is going to move downwards. This will create a current of hot and cold air, and in summers we actually see these wind blows, which is occurring due to this air current, right? This cycle of air current. At night, this cycle is actually reversed. We see that the cold air is coming down to the land, and hot air is being coming up from other regions. So we can look into these factors. There are several factors that cause these alteration of these currents, but in general, hot air is going to move up and cold air is going to move down. Why? There's a change in densities, and that causes these air currents to be there, right? Okay, so convection. What is convection? Right, we have discussed it's a circulation of particles around a container. So let's say we have a room in which we have a heater. In that room, we have air which is heating up the whole room. So hot air from the heater will move upwards, pushing air around the whole room, coming back towards the radiator to get heated up. So this is how the heating inside the room is going to work, and it will take some time to heat the whole room. Why? Because it's filled with air, so these particles will take some time to conduct energy from this heater to the whole room, while this current is the flow of particles carrying the thermal energy across the room, right? So the air closer, if you sit closer to the radiator, then you will be able to at point 1 it is going to be very hot, point 2 is going to be hot, point 3 is going to be a bit cold, and if you're somewhere closer here towards the floor, then you'll feel the most cold, right? Point 4, if I make one over here across. So this is going to be the gradient of thermal energy inside that room, and that is due to the convection, right? The convection current of the particles which are carrying the thermal energy, right? Similar way, in terms of cooling, since freezers are, we have refrigerators, they have freezing units as well. So it's just the cold air and the warm air moving around, exchanging the heat across these food products that we put inside our refrigerator to keep the temperature lower, right? Now the third mode of thermal energy is radiation, and this is the most unique one. It does not require any medium, unlike conduction or convection, right? It does not require a medium to transfer thermal energy. It is just a light form. These are photons carrying energy, and when those photons strike a certain surface, a different types of surfaces, it creates different thermal impacts on it, and that is how thermal energy is transferred from a light source to an object, right? And it does not require a medium as long as those radiations can transfer or travel through that material. It will heat up. For example, if I have a radiation heater, the ones we use in our winters, right, those which glow, and if you even if you put a glass between us and the heater, we'll still be able to get the heat from that radiator. While if we have yeah, let's say a hot air heater like the convection heaters, then we won't be able to feel the heat, because glass is a insulator, and it won't allow those since the hot air is not going to get to us, so we won't be able to feel the heat that quickly, as much as we're going to get the heat even through the glass using a radiation heater, right? So how it is transferred, we have this visibility range. This is now what we call as the radiation spectrum. So all of these radiations have their own different ways through which they are transported. Some are you can say able to pass through certain materials, some are not. For example, microwaves, they cannot go through metals. Visible light or color light, that cannot go through metals, but some of these, for example, gamma rays, they can actually transfer energy even through the metals, right? They can they're pretty much they feel transparent while going through any material, most of the materials, right? Because they are different kind of radiation. So different radiation have their own different you can say opaqueness levels at which they would be stopped, otherwise they'll pass through, right? We use radiation heaters to map these thermal images. It's a thermal image of a dog. Perhaps I don't know which type of dog, but is this a dog that is being taken as a snapshot through a thermal or a radiation camera, right? Now it is telling us which parts of the body. As you can see, there's a lot of blood supply to the eyes in an animal, so the eyes are lit up more, as well as the mouth, while since the skin is covered with fur, so fur is an insulator, so very less energy is flowing out of the body, so this radiation camera is not able to detect much energy coming out of the body, right? So this way we can easily detect which object is an insulator and which object is a conductor, using this radiation detector. So that's another thing that we're going to review just in a while. So how radiation works. In our case, sun is the radiation source. It is giving us the light during the daytime, which heats up everything. I mean, we need that light. Even the plants need that light to grow. So it's the thermal energy which is transported from the sun to us in the form of photons. And when these photons are absorbed by a surface, they transfer the energy that is coming from the sun, right? So this electromagnetic radiation, what we call as simply radiation, is going to be transferred through the vacuum space to us from sun to earth, right? Okay, now when we are talking about radiation, we need to understand there are two types of surfaces that we're going to discuss. One are emitters and the others are absorbers, right? Emitters are usually materials that are giving away radiation, while absorbers are the materials that actually take in radiation, right? They will receive those photons, and the energy is absorbed, while emitters are those which are giving out thermal energy through any process, right? So if we take out a category of material, then let's say we have a matte black surface, then we have a colored matte surface, then we have a white surface, and then we have a shiny or silvery surface like metals, right? Polished surface. Okay, in that case, the worst emitter would be the silvery and the shiny surface. Why? Because they mostly are the best reflectors. And reflection means if I throw light energy at them, right, or some radiation at it, it would reflect most of it back. So it won't be able to absorb the energy, so it won't be able to reflect that energy back, right? For an object to be an emitter, it should be able to absorb the energy provided by a certain light, and then it will be able to radiate that energy as well, right? If we give it some energy, or any electrical or thermal process, right? In similar way, white is a good reflector, white color. That is why we have some places which are hot, so white paint is preferred on the exterior, so that it reflects most of the energy and keeps the houses cool. Then we have these colors which do absorb a lot of energy compared to white, because when we talk about colors, we mean that only that specific wavelength of color is reflected back, rest of it is absorbed. And then when we talk about a black surface, that's the best absorber. Why? Because black color actually absorbs all light, and that is why we see black, since no colored light is reflected backwards, right? Moving on, we are going to look into this experiment just that I was explaining, that we have a Leslie cube, right? This is an instrument in which we have one black surface on the top, silver surface on one side, and white surface on the other, and we take a radiation meter, right? We simply fill this cube with hot water, right, boiling water, and we take snapshots on three sides, right, and we will find that black surface is going to be the in terms of emission, is going to be the best emitter, while these surfaces white and silver are going to be the worst emitters, right? But if we take the energy being absorbed, if we do not fill this with hot water and instead put light on the outside, we'll find that the silver surface is going to be the best reflector, the white surface is going to be a good reflector, but this black surface will heat up faster. Why? Because it is able to absorb heat much quicker. So this is one experiment. It's actually I use this as two-way experiment. This is Leslie cube was actually designed to just see emitters and absorbers, but the same cube can also be used to identify whether we have a reflector or an absorber of light, right? If you just keep it empty and put light from the outside, and see how it reflects the radiation using radiation meter, right? Another experiment that we can do is that we take a thermal radiation heater. In the middle we take two metal plates. One, we polish it up, we make it look silver, and the other piece of steel we just paint it with matte black paint and we put them at an equal distance from the center, right? We take a meter rod, and then we separate them at equal distances, right? Let's place a meter rod over here and keep these surfaces, two metal pieces at equal distances from the middle of this thermal radiator, and then we have this thermometer attached to both these surfaces, and we'll find that once we turn on this radiation heater, this shiny surface, since it is reflecting most of heat back off, right, so it will rise in temperature much more slower compared to this matte surface, which is absorbing majority of the radiation which is coming from this radiation heater, and the temperature over here will rise much more quicker, right? So this is one experiment we can also use to identify which surface is a good absorber or not, right? So our last topic of this block is thermal radiation of Earth. So we're going to look into how solar energy is coming and what it does for us on Earth, right? So solar radiation or energy from the sun is coming to us in terms of photons through the space, and once it's entering through a clear atmosphere, it comes down to the surface of the planet, and over here most of the radiation is absorbed by the surface, and it warms the surface up. And if we do not absorb, if Earth was not able to absorb that energy coming from the sun, then the overall temperature of the Earth during both summers and winters would be 25 degrees lesser than the current temperature variations that we do have, right? Let's say if it were summer, it would be just 25 degrees instead of 50 in our region, and if it were winter, where we have about usually 1 to 2 degrees Celsius temperature in the winters, it would be about minus 23 or 20 degrees Celsius in winters. Why? Because the solar energy from the sun is no more here to heat the surface of the planet, right? since we are very close to it, but this is how the temperature is going to be affected if that energy is not being absorbed. Now, some of that energy is also reflected back from the surface and the atmosphere. So when we talk about radiation, then it is usually reflected back in terms of infrared radiation from the surface of Earth, right? Uh, this is the effect when these, even the reflected radiation goes out, but most of the time it is also reflected back by the atmosphere into the surface, keeping the overall temperature retained, right? The radiation energy from the sun being retained during the day, so that when at night it's the colder, region of the earth, it still retains some of its temperature, right? This is what we call as the greenhouse effect, right? The thermal energy coming from the sun is entrapped inside the atmospheric layers, right? This is what we call as greenhouse effect. This is also experienced, this is actually utilized by herbologists or plantation experts, where they're growing special plants in colder environments, but they need heating, so they utilize the sunlight and trap it using these glass panels, right? In a closed off box, and such that the light radiation that comes in, which is keeping the air inside the environment inside this house, the plantation house, it will keep it warm, and we will be able to grow plants which are usually not able to grow at lower temperatures, right? Why? Because the temperature inside this building is going to be warmer as compared to the outside. Why? Because we have entrapped thermal energy in there. This is called greenhouse effect, right? This is also happening due to certain gases which actually retain thermal energy, and they don't allow this radiation to go outside, or it reflects the thermal energy, the radiation within that layer of atmosphere, which in our case is actually carbon dioxide, which we call as the biggest reason behind global warming, right? Mostly produced due to combustion of fuels, right? We also breathe carbon dioxide, but that most of it is actually recycled by plants and turned into oxygen. But since we're also using fuels and we're burning a lot of carbon into the air, so carbon dioxide is there, which plants are not able to actually absorb that faster. We don't have enough plants. That is why we were having these plantation drives, so that we recover from this situation of excess carbon dioxide, which is now retaining more energy from the sun, causing the overall temperature of the planet to rise, which we call as global warming, right? So this is also called as the greenhouse effect, but this greenhouse effect, since is now attaining some adverse, it's posing some risks towards the sustainability of the planet, so we call it global warming, right? And this is one big major issue that is under stress by most of these countries, and people are working, the institutions and the research institutions, manufacturing factories, all of them are working together to fight this global warming effect. That is why you see these electric vehicles coming to the market. Why? Because fuel burning is the major cause in this increase in temperature due to excess carbon dioxide in the atmosphere, right? So overall, we have discussed how conduction works, how thermal exchange works. I hope I'm able to, transfer most of the ideas that are there, the understanding of the topic, and how these, processes of thermal exchange are occurring. Thank you so much. Bye bye.